In this video, I will discuss the relation between LTI system properties and the impulse response. We know that the impulse response completely characterizes the input-output behavior of an LTI system. Hence, the properties of the system such as memoryless, causality and stability are related to its impulse response. Now let's study these properties one by one. Let me consider memoryless LTI system. We know that output of a memoryless LTI system depends only on the current input or present input. Let me consider an LTI system which has input say x of n and y of n be the output. Let h of n be the impulse response of this system. In this case, the output y of n can be represented as x of n star h of n, that is x of n convolved with h of n, which is also equal to h of n star x of n. So convolution between two sequences can be mathematically represented as y of n is equal to summation k minus infinity to infinity h of k x of n minus k. So already we have studied this in my previous videos. Let me call this as equation number 1. Now let me expand this summation. Expanding this summation, so I can write y of n is equal to, as we know k varies from minus infinity. Let me start with minus 3 samples. So let me take k is equal to minus 3, that is h of minus 3 x of n minus of minus 3. It will be n plus 3 plus next sample will be minus 2 h of minus 2 x of n plus 2 plus h of minus 1 x of n plus 1 plus h of 0 x of n plus 0 is nothing but n minus 0 is n plus, let me continue here. So after 0 we have positive samples, that is 1, k is equal to 1, that is h of 1 x of n minus 1 because k is equal to 1 plus when k is equal to 2 we'll get h of 2 x of n minus 2 plus when k is equal to 3 we'll get h of 3 x of n minus 3 and so on. So now this system to be memoryless, the output y of n must depend only on x of n and cannot be depend on x of n minus k at k is not equal to 0. So now in this equation we can see that x of n plus 3 is future values of x of n. This is also future value of x of n, future values of x of n, whereas x of n minus 1, x of n minus 2 and x of n minus 3 are past values of x of n. So for the system to be memoryless, y of n must depend only on x of n but not on x of n minus k at k is not equal to 0. It means that, so therefore these all terms should be 0, so that the y of n depends only on this term, that is h of 0 x of n, where x of n is present value of x of n. Therefore we can say that Here h of k will be equal to 0 when k value is not equal to 0. So this is the condition for memoryless LTI system. So thus we can say that a discrete time LTI system is memoryless if it is of the form h of k is equal to c delta of k. So here we can see that delta of k value is 1 only when k is equal to 0. If k is other than 0, then h of k value will be 0. Thus the condition for memoryless is h of k is equal to 0 when k is not equal to 0. So therefore similarly for continuous time signal, the condition is given by h of t is equal to 0 for t is not equal to 0. This is the condition used in continuous time LTI system. Now let me consider causal LTI system. We know that the system is said to be causal when its output depends only on present and past values, but not on future values. So here we can see that x of n plus 3, x of n plus 2 and x of n plus 1 are future values of x of n, whereas x of n minus 1, x of n minus 2 and x of n minus 3 are past values of x of n. So for the system to be causal, output y of n should depend only on x of n minus 1, x of n minus 2 and x of n minus 3, but not on future values, that is x of n plus 3, x of n plus 2 and x of n plus 1. Here we also observe that these future values of x of n is associated with when k value is less than 0, and past values of x of n is associated with k values when k values is greater than 1. Therefore we can say that to make y of n to depends only on present and past values, the required condition will be h of k must be equal to 0 for k less than 0, because when k value is less than 0, then we can see that those all are associated with future values. When k value is greater than 0, those all are associated with past values. Therefore we can say that h of k value should be 0 when k is less than 0. This is the condition for causality. So in this case we can write y of n is equal to summation k is equal to 0 to infinity, because it starts from 0. If the value of k is less than 0, then system will be 0. We can write it as h of k x of n minus k. So similarly, the condition for continuous time LTI system is given by h of t is equal to 0 for t less than 0. This equation can also be represented as h of n is equal to 0 for n is not equal to 0. That is, impulse response of the system h of n is equal to 0 when n is not equal to 0. The system is said to be memoryless. Can also be represented as h of n is equal to 0 for n less than 0. This is the condition for causality in case of discrete LTI system, and this is for continuous time LTI system. Now let me consider the third property, that is stability. We know that an LTI system is bounded input, bounded output stable if and only if its impulse response h of n is absolutely summable. That is, we can write the condition as summation k is equal to minus infinity to infinity h of k, the value of this must be less than infinity. Similarly, for continuous time LTI system, the condition is given by integration minus infinity to infinity h of tau d tau, its value must be less than infinity. So let me take one example so that we can understand these properties very well. Let the impulse response of the system is given by h of n is equal to half power n u of n. Now let's see whether this system is memoryless, causal or stable. That is, verify the given system is memoryless, causal and stable. So let me take the first condition or first property, that is memoryless. So here we know that the condition for memoryless is h of n must be equal to 0 for n is not equal to 0. This is the condition for the memoryless system. So now in a given system we have h of n is equal to half power n u of n. Now let me draw the h of n signal. So here I am drawing signal for understanding purpose. So let this be h of n, say this is 0, at n equal to 0 the value will be 1, let this be 1. So this is 1, 2, 3, 4 and so on. Let this be minus 1, minus 2, minus 3 and so on. So now when n is equal to 1, the value will be 1 by 2. When n is equal to 2, the value will be 1 by 4 and so on. So now here we can see that h of n value is not 0 when n is not equal to 0. That is, for n is equal to 1 or n is equal to 2 or n is equal to 3, the value of h of n is not equal to 0. So here h of n is not equal to 0 for n is not equal to 0. Therefore, system is not memory less. Let's consider the second condition, that is causal. We know that the system is said to be causal when h of n is equal to 0 for n less than 0. So here we can see that h of n value is 0 when n value is less than 0. Therefore, the given system is causal. Therefore, the system is causal because h of n value is 0 here. When n value is negative, its value h of n is 0. The third condition, stable. The system is said to be stable when the summation, that is k is equal to minus infinity to infinity mod of h of k, if it is less than infinity, then we can say that the system is stable. Let's verify that. So here I can represent this h of n as summation, as it is varying from 0, that is k is equal to 0 to infinity h of k, or I can represent it as summation k is equal to 0 to infinity. H of k is nothing but half power k, half power k. So this can be represented as 1 upon 1 minus 1 by 2, which is nothing but 2, which is less than infinity. Therefore, system is stable. Thank you for watching.